Should we start? Yeah? I know it's not requisite 10 minutes over at NASA, but...
No, that's fine. Well, I have a 2-hour talk, so we better start.
Yes, Kostas.
Okay.
Please begin.
So I'm going to present you the new model development I've done the last few months, maybe a bit more than that. And that includes, it's the first step towards the coupling of atmospheric aerosols with the ocean biology. So the idea is that what all models are assuming until now, maybe until a couple of years ago, I would say 100% of all models that have oceanic aerosols were always having seasol. So oceanic aerosols is seasol pure, and although we know there are some other components in it, all global models were using seasol, sodium chloride, as the component of sea spray. And but since I mentioned sea spray, what exactly this is? It's if you think of this as the ocean surface or any water surface that includes it's not fresh water. It has a lot of bubbles in it. So these bubbles go all the way up, and then they reach the surface and they pop. And while popping, they create these film drops here. And then after this film drop, a layer of water comes upwards and creates these jet drops. So there are the main two differences between these two is that first, these ones are really tiny compared to these ones.
Isn't there spume? There's a whole bunch of ways of making it. Right? You have when the tops of white caps tear off and that's spume or something like that?
Yeah, white caps are also something that I will mention later. So this is for the calm layer. So, and then the other thing to mention is that these drops here come from the really thin layer of the surface of the ocean right here, although these ones come from a bit deeper. And there are several important implications about this mechanism, and I'm going to present later on. And as Andy mentioned, there is this happens only when the ocean is calm. When there is wave breaking, that you have the white cap fluxes, then this is a different story, and I will roughly present something about it. So why do we bother about sea spray? Sea spray, when it's emitted, has a lot of humidity, a lot of water in it, and then it evaporates and creates aqueous droplets, aqueous aerosols that primarily consist of seasol. And so these aerosols, then the aerosol composition of these particles here is affecting the cloud formation potential of them. So if they are purely seasoled, or they are seasoled covered with something else, they will have different CCN activity, and they will not have so big effect in the cloud formation. And then, if you change clouds because of that, you affect the aerosol formation because you change the climate underneath, and then you change the fluxes because the bubbles are also depending on the wind speed. The way that you produce sea spray is also depending on wind speed. And so you affect the source directly. You can, by changing the clouds, you can also affect the removal of aerosols, and you can, and then by having aerosols with a certain composition dissolved into cloud droplets, you can affect the cloud droplet properties, the cloud properties, and the cloud lifetime. So there are a whole lot of things that are interesting to study here, and we're just scratching the surface in this talk. And you will see that there are more uncertainties than certainties, and you will also see that I hope I will convince you that the reasons why we cannot model properly the oceanic component of aerosols coming out from the sea is not because of the uncertainties in the oceanic source. So let's go first to the sea spray source, no matter its composition. On the x-axis here, you can see the size of aqueous aerosol emitted at relative humidity of 80%, and on the y-axis, you see the effective flux of the effective number flux of particles. So the more you decrease the aerosol size, the more you increase the aerosol number, and wherever the solid line is where it is significant, and then the dashed line is extrapolation. And same with the dark and white shade here. So these are 4 different approaches. The Monahan is the one that is an approach that first came out in the literature, something like earlier than the 1986 that I'm presenting you here. And then the Gong is an updated one of the Monahan parameterization. And then on top of it, Jaglé is a parameterization that takes the Gong and applies a surface temperature function. So you take a range depending on how cold or warm the sea is. And in general, the colder the sea is, the less sea spray you get. And then there is also the Lewis and Schwarz parameterization, which is first of all, you see that it's really different here, and the reason is that it comes from a completely different approach. And the most important thing between this group of our parameterizations and this one is that the Lewis and Schwarz produces way less particles in the submicron range and way more in the supermicron range, and this is a log normal. So this small difference is close to an order of magnitude. And so in model E, there are 2 size classes for CISL, which is one is the submicron, which is someplace here. I doubt you can see this limit here, but it goes up to 0.2. And then there is the supermicron, which covers this size range. So by starting from close to the end, just simulating what the model can do based on these different parameterizations and compare it with measurements. So we have the Monahan, we have the Gong, we have the Jaglé, which is this one produces that. This one is an evolution of that, and this one is an evolution of that. We have the Lewis and Schwarz that produces much more aerosols, as you can see, since most of the points here are above the 1x1 line, and this is because this parameterization produces many more coarse particles, which dominate the mass. So you get, since this is a mass by comparison, you get much more mass. And then this is the Aerocom. This is a source that comes from Aerocom. It is based on Gong, but it covers a wider range of particles. It's also offline. And then this is also a comparison with horizontal winds nudged, which are a bit. They are really different from what the online model. That's why you have some differences. And there are something like 20 stations around the globe with very long-term measurements of sea salt that we can take the climatology and compare with the model. So I'm just picking up only 2 here, 2 pretty good ones, I have to say. And one is at the university, close to the University of Miami, and the other one is at the west coast of Ireland. And first of all, you see that different approaches tried here agree in general mostly well, except the Lewis and Schwarz, which I will not discuss too much because we have this discrepancy for the coarse sea salt. And same thing with Macehead. So in order to really see which one of them does better, we compare the measurements against the model results by using Taylor plots. And I believe that not many of you might be familiar with this one, so I'm trying to explain. So just focus here. Both the x and the y axis present the normalized standard deviation, either measurements or model. The arc here presents the correlation. So the more, if you follow these actinic dotted lines, the more you move downwards, the more higher correlation you have between model and measurement. The ideal measurement is here, this white circle. So it is the point that the normalized standard deviation is 1. So the standard deviation of the model and the measurements is the same. And then it is where correlation also equals to 1. So it has a perfect correlation. Of course, there is no ideal model. And so all of them are spread throughout this place. And you can see that when you are away from this arc that connects the one here and the one there, the further out you are, the more standard deviation has the model against the measurements. So it has much higher variability compared to the measurements. And the more you are away based on this dimension, then the less the correlation.
I have a question. So in your motivation stuff, it was all about numbers, right? It was all about clouds. And I would have thought that therefore you care about numbers, not mass. Why are you focusing on mass?
I'm focusing on mass because the model calculates the mass. And so it's a further step will be eventually one day to have the aerosol microphysics doing that thing. But for now, since we are using the mass-based model, we just take the two different size bins that they are extremely different optically, first of all, plus other things like removal, etc. And by assuming a certain number for these, we take the fluxes and then we calculate whatever the models calculate.
So what your data looks much more correlated in the 4 to 8 months versus, I mean, in theory, with the model and the data. So how does that change? Like if you look at these, it looks like some of these models don't fit very well for months 1 and 2.
Yeah.
So what if you change that? How does that change that? If you just restrict yourself to the months where it fits best, how does that change this correlation plot? And then vice versa, if you change it the other way, will they get completely unequal?
Things change depending on what data you select to.
What I'm saying is you have a lot of garbage at some months, and then
not necessarily.
That's going to influence your correlation.
That's not persistent throughout the stations. So for example, here you see that these ones are really off, but here maybe this place is really off, or this one only, but not here. So it really depends on the station. It's not. You don't see a pattern in these things.
But it doesn't have to do also with temperature, because you were just saying when you go Miami is much more
you
water
go too fast.
than.
You go too fast. You go too fast. I'll go into temperature later.
Kostas, why do you have differences between GONG and GONG with oceanic OA, for example?
I'll also go into that.
Is there any are these in surf zones?
These are surface. Everything is surface.
Surf. Where surf is breaking, is that a problem? I mean, most of the ocean doesn't have, waves crashing on shore.
That I'm not sure whether that can be answered right now. So.
But for these two places, can it be answered? Because Miami is what he said, it's near shore, and the same with this Ireland place. So this is shore-based, in a sense. It's biased.
Sure.
Okay, just asking.
Yeah. Sure. But it's tricky though for Macehead. Macehead is a very strange place for the model because it is exactly at the border of two grid boxes. But one of them is almost completely oceanic and the other one is almost completely land. So it's a really tricky place. And I didn't want to say that these two are representative to some results or something. It's just two good stations that I'm trying to show you how the model comparison.
I might have thought that you would have trusted the nudge because you think these are wind speed dependent, these large kind of particle size distributions. Mm-hmm. I would have thought that the nudged horizontal winds would be like a better base state, but I guess you don't think they are. I wondered why.
No, they don't appear to be, no. And
so do your winds match the observed winds better in the cases where you didn't use nudged winds?
First of all, for the let me remember how I did the nudged winds. Because these concentrations that I'm presenting here are climatology, not from specific years. And this climatology can come from something like 10 or 15 years ago. and I compare with something more recent. So other factors might contribute to some difference. But either way, the nudged winds compared to the model's winds are different, but not that different. And the model is very sensitive in calculating the size, the total mass of sea salt emitted by the ocean. It's really sensitive. So changing the winds by something like 10 or 20% will not necessarily change the concentrations by 10 or 20%, because the mass is dominated by size, and the bigger aerosols you have, the faster they sediment. So there is a whole lot of other processes that affect the final distribution of sea salt. And I'm sure that you will have a lot of questions at the last couple of slides that I'm going to show you, that they will also include clouds there, and wind speed, and sea salt, and everything. It's a really tough thing when you start comparing with sea salt.
Yeah, there's one more issue, which is that you're only nudging the winds like 4 times a day, every 6 hours.
Mm-hmm.
And obviously there's a lot of gustiness in the winds. I mean, in the real world, the winds are changing constantly, and just because, as you mentioned, these aerosols are highly dependent on wind speed, you really have this nonlinear or a very disproportionate effect. A very strong gust of wind can actually put up a lot more aerosols into the atmosphere than kind of a steady wind, and so that's something obviously you're not getting out when you just restore the winds 4 times a day. Yeah. So that's something else. We have a parameterization like that for dust, and you might want to think about putting that into your calculation for the sea salt aerosols.
Yeah, and especially concerning the gustiness, this also is heavily resolution dependent. So since this model is 2 by 2.5, if you go down to 1 by 1, gustiness will be very different, and it will affect the sources a lot, just because of the changes in the wind speed at smaller places. And I guess the same applies to dust, right?
Well, for us, I mean, I think most of the gusts of wind are happening on the time scales of minutes, or over spatial scales that are much smaller even than a 1 by 1 grid plot. So in that sense, we're not really anywhere near resolving those. So again, that's something we just have to parameterize.
No, that's a really hard thing to do. So, okay, so so when you see this plot, and the distance from this plot to every dot is the root mean square error. Just to finish with this plot. So you can see that there is quite a lot of scatter, and some other stations are a bit better. There are some stations that look like that many of the points are really close to this 1.1. And there are some others that you can hardly see any points because they just go out of the slide. So it's really a big scatter. And here are where these stations are, and you see that they are all over the place. And by trying to figure out why there are certain differences, I was really trying hard to figure out what's going on. I mean, what is this thing here that persistently appears in no matter the calculations, or also this one. So while trying to do that, I got from Joe Prospero, I got some extra data showing the quality of the measurements per station, and then all questions were answered. Number one, this station here, it's based on the station quality data. It says that it is heavily affected by strong katabatic winds from the continent, which means that for that station, you should take into account that this is primarily continentally influenced, not oceanic. So there is no way for the model to get a continental influence if you average over a 2 by 2.5 degree grid box. So that's why the model heavily overestimates the measurements. And then,
but you compare the sea salt.
Yes. So sea salt, I'm comparing sea salt. So this one is heavily oceanic influenced, so there is hardly any sea salt. That's why the measurements are down here. And the model is taking the average that includes some part of the ocean, and it calculates much more. And so for this one, all these points here, it was absolutely impossible to figure out why they are different. And then the station quality report was saying these are bad measurements. So I don't think that I should even worry about
The
it.
solution is that you have to go visit them.
They are in nice places, you see. I wouldn't mind going there. And then, from the other stations, there was not a persisting pattern. But what you can tell is that throughout this region, which is the most windy region of the globe, except Tasmania for some reason, the model in general overestimates measurements. And this is because it is way too windy. So maybe the source function of for such a windy place is not proper, maybe the removal is not proper. But we knew that this region here is a very challenging one. And so that's only sea salt. But as I told you, sea spray is not only sea salt, it also has organics. And very recently, a lot of attention has been paid on that organic enrichment of sea spray. And you can see that there is a loose correlation between the percentage of organic mass on sea spray versus the chlorophyll concentration at the surface of the ocean. So this is, we try to take this loose correlation and apply it into chlorophyll from the satellites, use the source function of sea spray, and then by replacing this equation with a newer version of it, we try to do, to see how much, first, how many organics are being emitted from the ocean, second, whether they affect aerosol properties that they are, and how they affect cloud properties, etc. And that's, you'll see some results later. So, in order to start answering some of the questions being posed already in the slide number 2, this is the organic enrichment versus size. So you see that there is, when you have very small particles, the enrichment can be as high as 70%, meaning that 70% of the sea spray for these size classes is organic aerosols and not sea salt. And then when you go to coarse aerosols, virtually everything is sea salt and not organics. And this is related with what I just showed you in the first slide. The organics are mainly in a thin layer at the top of the ocean, and not so. And there is an enriched organic layer up here compared to the bulk oceanic mass, and that's why everything goes to the fine mode. And then, what Andy asked is about the wind speed and in general how the wave breaking affects the fluxes. This is something that is not included in the model yet. And what these authors say is that the plot is qualitative but not quantitative and is not supposed to be used in global modeling studies. They clearly say that in the paper. So, but the idea behind it is that when you have very low wind speeds, there is no wave breaking at all. So all bubbles that come out pop up like this, let's say ideally. And so you have the enrichment is as high as possible. Then when you move to extremely high winds, you have the wave breaking, and this enrichment is, this layer in the top of the ocean is much more mixed, so that you don't get high enrichment. And there is also an area in between. So I'll come to that. How does the model compare spatially? For sea salt, there are a lot of measurements throughout the globe and very long term. For organic carbon in the remote oceans, it's extremely difficult to find measurements. So this is a collection of measurements mainly from ships, and although I'm showing you in the background with the color the annual mean of the model for the total organic carbon, the points here are most of the cases just a single month or just a single point. Because, for example, this one is a ship cruise that went all the way like this, and they were collecting from one place to the other something. There is only one data point, which is better than no data point, but still it is not directly comparable. My point is that when comparing the measurements with the model, the proper month of the model in this case, not the annual mean, so this comparison is much more quantitative, you see that the model heavily underestimates all these measurements. But when you include the oceanic organics as calculated by the model, not everything gets better, but it really gets much, the comparison really goes at least close to the 1 by 1 line. And so that was a very encouraging thing. And if you go to certain stations, you see that in various places around here, you can see the single star in all these things, which is the measurement of the organic carbon. And then the colors represent the different components of organic carbon, with the blue being the oceanic one. And you see that in most cases, the measurements were really far away from, if you don't include this blue part, then the model cannot calculate not even the magnitude in some cases, like this, like here, and or even here. But when you include the oceanic organics, the model does a much better job. Of course, we need a much longer term measurements to be able to know whether the model is doing something proper or whether this is just a coincidence. And this is how many, every line here is, it's exactly the same stations, but every line presents different models. And although there are some places like here, Miami, that because of pollution there is a high variability between models, in really remote places like here, you can see that no model is able to capture this data point, but the GISS model that is, includes the oceanic organics. And the same applies to here. And here you can also say that, and if you exclude this model which does this funny thing. And not all news are good though, because there is Amsterdam Island here. This projector has a really poor grayscale, right? So it has this. So this is the globe here. But I don't believe you can see it. And Amsterdam Island is at the south of the Indian Ocean, and you see that these are the measurements. These are the other models in general underestimating, and this is the GISS model. And there are some reasons to explain why this is happening. One is that exactly this region here is where the model is calculating the highest wind speed on the globe. And so the source function of sea spray is the highest ever. Second, we don't have any, if we believe that when you have extremely high wind speed, then the enrichment of organics is not so high. This thing is not included here, and this will take this line much further down. And it's puzzling, because this is a station that it has something like 5 years of measurements of organics. And it's really a pity that it's in that very unique place in the world. And and there is this gray model here includes oceanic organics, the line that goes almost straight. And also this green line here includes oceanic organics. This brown line doesn't. So yeah, just mention that. So if this place is mostly here, then we're just using the wrong function for the enrichment.
Does the film form instantaneously?
No, it's just accumulates.
So it's not just wind speed, it's like wind speed over the last weeks?
No. The film over the ocean is just accumulating based on how life performs under the surf. So
Go ahead, take it.
So the surface layer is enriched because these organics are mainly hydrophobic, so they just lift up gradually and they just stay there because there is nowhere else to go. And then, but the wind speed is instantaneous. So the moment it blows, it swipes the ocean surface and takes whatever was accumulated there.
So there's a little bit of a time function in building it up, but not removing it.
It should be. It's not studied though. This is what they believe, but it's more like what it appears normal to be. So, again, focusing on this southern ocean, the zone between the band between 30 and 60 south. This is the optical depth calculated by the different versions of the model based on the different functions. And this is fine sea salt. This is coarse sea salt, organic aerosol, total organic aerosol multiplied by 10, and the total aerosol. First of all, I'll start with the coarse sea salt, which is the easy one. You see this striking peak. This belongs to this line here, as I told you before. The Lewis and Schwartz calculate many more coarse sea salt, so that's why you have this peak that appears also in the total. Second, for the same reason, you have this small peak here for the fine. Second, all these four belong to a group of simulations that have the same coarse or sea salt function, and all these three they have the Jaglé that includes the sea surface temperature dependence. So that's why they differ, and there is no discussion about oceanic organics in the coarse sea salt fraction. So these are not so much affected, but the only changes here are mostly because of the underlying climate changes that happen between the simulations. For the fine sea salt, depending on what source function we're using, you would expect that this is the case for fine sea salt, but because you have the oceanic organic enrichment, you have some more important changes here that they depend on that. And the oceanic organic are from these two, which is the gong, is higher than these two, which is the Jaglé, and this is because they have a difference in the temperature, on the sea surface temperature. And this rise from this line to this line is the difference because of the oceanic organics, and the same from here. And this is a total, and in general it's higher than satellite measurements. And I still believe it's a matter of wind speed and the sea spray function, and I'm trying to figure out whether there is something to do there. And if we take some statistics, you can focus on the standard deviation, for example. This is the standard deviation of the measurements, and these are all the different approaches I used. And mostly, in all cases, the model shows a higher variability than the measurements. It shows the mean of the measurements in general is kind of okay compared with the measurements. And the correlation changes with depending on the source function used. And there is this plot here is the one that tells us that we really don't know what's going on here. Because when the formulations for the sea spray source function were evaluated, they were taking climatologies of sea salt and saying, okay, I have this sea spray function, everything is sea salt, and then I compare with sea salt, tune a bit, and then this is my function. And this is what all models, including the GISS model, are using. When using the oceanic organics as well, there are two cases. One case is that sea spray has part of the sea spray is organic, so sea salt is less. So you should go from the red one here, which is the gong, you go to the green one, which is the oceanic organic source, and you see that there is a small improvement in the correlation because we included the oceanic organics by reducing sea salt. but the sea salt function is tuned based on the sea salt measurements we are using. So that makes no sense. But when we go to this line here, that we don't reduce sea salt, we just keep sea salt as it is, and we say, okay, there is the oceanic organic enrichment, so we just introduce an extra mass of organics instead of using instead of changing the sea salt function. And you see that the correlation goes even worse. And this is really challenging. And if you go to the Jaglé set down here, which is from a fairly poor correlation because of compared to the gong, introducing the oceanic organics by reducing sea salt doubles the correlation, and then by not changing sea salt but introducing the organics affecting climate, of course, then reduces the correlation, but of course improves it from here. So this means that maybe the noise of the system is so very high, maybe we really don't know what these functions are doing. Just to wrap up the budget, before having sea salt before having any oceanic enrichment in sea salt, these were the numbers: 300 to 350 teragrams per year for the fine fraction of sea spray, and it was giving that lifetime. By introducing the oceanic organics, which are about 70 teragrams per year, then sea salt has an increase. The fine sea salt is the line on top, and coarse sea salt is the line on the bottom. So the lifetime of sea salt is increasing because the oceanic organics are mixed with fine sea salt, and they are less soluble. So they are being removed less efficiently. And the scary thing is when you try to compare these numbers with other numbers published in the literature, that you see for the oceanic organic source, you see numbers from 8 to 75. And for sea salt, you see numbers from 6,000, from 2,000 to 6,000. And what really happens though here is that the more fine sea salt the models have, the more oceanic organics they calculate. So for example, this model here that I know very well, since I'm also in the co-author list, has about 60 teragrams per year of sea